So since we're starting into organic chemistry, I want to take a second to review a subject that you guys learned last year, and that is the drawing of what are called line angle or skeletal formulas. Okay, so whenever you're drawing organic molecules, you end up drawing lots of carbons and also lots of hydrogens which are connected to those carbons. All right, and because of that, it can take quite a long time to draw these molecules if you're going to draw in all these things. And there's this little shortcut to drawing these molecules which is called a line angle structure. All right, so over here to the side is just a quick way to interpret them. It is assumed that there is a carbon at either the blunt end or the intersection of line segments. All right, and after you realize where the carbons are, your job is to add hydrogens, or to assume that there are hydrogens there that are not drawn, so that you eventually get a bond total of 4. All right, so let's start with this molecule right here. All right, actually let's go the other way. Let's start with this line angle structure. All right, so what you see is a couple of line segments. You've got an oxygen here, and then you've got another line segment going on here. All right, so first of all, if there's a regular atom drawn in, it's obviously that atom. This is an oxygen. So anything other than carbons and hydrogens you have to draw in. All right, but coming this way, I see an intersection between line segments. Okay, so there would be assumed to be a carbon there, and this right here, this is a blunt end of a line segment, so there would be assumed to be a carbon there. And this end right here is the bond to the oxygen, and going out this way, that would be assumed to be a carbon there. All right, so what this means, so here is the oxygen. There are 2 carbons in a line. Those would be this and this. All right, and the last thing that you've got to do is you got to realize that there's missing hydrogens. All right, well, currently at this carbon, I see 1, 2 bonds, so there are assumed to be 2 more hydrogens. All right, so there would be 2 hydrogens off that carbon, and I drew these hydrogens on opposite sides. They're still attached to that carbon there. If I were to draw it with this little kink right here, I would probably draw them on top. All right, as you'll see in a little bit, it doesn't really matter whether you draw it like this or like this. All right, so to this guy right here, there's currently 1 bond which is drawn, so there would be 3 assumed hydrogens, so those would be right here. And again, there's only 1 bond to that carbon, so there's 3 hydrogens right there. All right. So keep in mind, if I had put something like a chlorine, a bond to a chlorine right here, just change one of these to a chlorine. But if there's a chlorine right here, that would mean that there are 1, 2 bonds to that carbon, and you'd only put 2 extra hydrogens. All right. So let's start with this line angle structure right here. This one looks a little bit different. Okay, so first of all, that's obviously oxygen and that's hydrogen. And you might be wondering, I thought we don't put hydrogens on these. All right, you don't put hydrogens which are attached to carbons. All right, generally, if it's a hydrogen attached to anything other than a carbon, you go ahead and draw that in. All right, so here's an intersection right here. So there would be a carbon here. This one, hopefully you recognize this is a double bond, which is intersecting with a single bond right here. So there would be a carbon right there, and this is a blunt end of a double bond. There would be a carbon right there. So draw, if you're practicing this, draw in your carbons, and then just go back and draw in hydrogens so that you get up to that total of 4 bonds per carbon. All right. So here you've got 1, 2, 3. All right. So when you're doing this, that double bond counts as 2 separate bonds. So 3 bonds are shown there, so that would mean that there would be 1 more hydrogen shown off this. All right, so I'm going to come back and say something about this in a second. Let's go and look at this molecule right here. All right, so we've got, all right, this is a blunt end. There's a carbon there, there. Okay, this one's a little interesting. This is a single bond coming in this way. This is a triple bond coming in this way. So I didn't mean for there to be a gap right there. There does look to be a gap, but like a lot of times when you're showing this single bond coming into a triple bond, you leave a little bit of a space so it doesn't look like one continuous line going across there. All right, because they are two different bonds. All right, so carbon right there, and that's a chlorine. All right, so with this triple bond, you can count with each of these sides. There's 1, 2, 3, 4 bonds. All right, so there are no extra hydrogens to draw on these carbons right here. This has got 1, 2, so I need to draw in 2 more hydrogens. All right, this one right here, there would be a hydrogen right here because there's 1, 2, 3. All right, and there's your extra hydrogens. All right, so one thing I want to point out about this is that you need to realize, okay, if I were to draw a, if I'm drawing the carbons and hydrogens in, all right, obviously you can tell that there is a carbon right here because it's drawn in, all right. But notice the way I've drawn this. This bond and this bond make about a 180-degree angle, all right. So if I were to try just to do the line angle where I'm joining segments, well, if I draw 2 line segments with a 180-degree angle, well, what does that make? It appears to be one long straight line. All right, so whenever you're doing these single bonds, all right, whenever you're joining 2 line segments which are single bonds, you always want to put a kink in there. All right, and that's to indicate, that's to make it visually obvious that that's an intersection between line segments. All right, so going down to this thing right here, this is a double bond, and this is a triple bond. And one thing that you hopefully noticed is that when I drew this double bond, I didn't draw the line segment coming straight out from it. I drew it coming down so that this is approximately a 120-degree angle. All right. With this right here, I drew it. Notice I didn't draw this chlorine kind of down at an angle, and that's done deliberately because when you think about the angle geometries, okay, this one right here, so this carbon right here, this would be trigonal planar. All right, that's the geometry around that double bond carbon. All right, so this is 120, that's 120, and that's 120. So whenever you're drawing these line angle structures with double bonds, you want to try to approximate the true correct angle. All right, even though when we're drawing molecules, sometimes we're not going to be able to draw the true shape because a 3-dimensional shape on a piece of paper is sometimes impossible. But as much as possible, we do like to try to show the angles that would really exist. All right, so you never draw a double bond with a line coming straight out from it, nor do you do it with a 90-degree turn. All right, you tend to try to make that 120-degree angle. All right. So with this one, we know that's 180 degrees. That's why you draw these straight across. So just a little bit of advice. A lot of times when people are learning this, it's a lot easier to go from a line angle to a regular structure because I can take this and just draw in my carbons. I could draw the carbons in over top and then just fill in the extra hydrogens. All right. People tend to have a lot tougher time when they go from a regular structure back to a line structure. And I want to give a little bit of advice on this that I think is it covers the main mistake that people have. All right, at least when you're first getting used to this, when you take your regular structure, scratch out the hydrogen and the bond. All right, notice I say not just the hydrogen, of any hydrogen which is bonded to a carbon. All right, so let me show you why I think that helps out a lot. Okay, so what I've shown here is actually what I advise against doing. All right, so what I've done is, and you can rewind the video and see what this originally looked like. This is just covering up the hydrogens. And this is what a lot of times people do because they know that they don't, in line angle structures, we don't show hydrogens connected to carbons. All right, and so with that in mind, they go through and they cover up the hydrogens. All right, the problem with doing this is that I can still see the bond. All right, there was a bond going from the carbon to the hydrogen, and I can still see that bond. And when I can still see that bond, when I'm drawing this structure over here, I find that a lot of people are tempted to draw that bond in because it's visible over here. Well, there's a problem with that. If I draw in that bond, all right, at the end of the bond, that would be the blunt end of a line segment. Right? And so if you were to look at that as a line angle structure, you would be tempted to think that there's a carbon there, and there really isn't. There's a hydrogen there. All right, so here's my recommendation on how to do this. Okay, so instead of covering up just the hydrogen, scratch out the hydrogen and the bond that is connected to the carbon. All right, so now when you're looking at it, you're only looking at the carbons, and you're only tempted to draw what you see. All right, so notice if I was doing this structure right here, when I was scratching things out, I would not scratch this one out because that's a hydrogen connected to an oxygen. All right, and the more you do this, the more it starts to become more natural, and it's really quick just to look at something quickly and figure out how many carbons are in there, and to notice where the missing hydrogens are.